All right, so let's start up. I am unhappy to say that the star of the show, who would be following me, Fatih Guvenen, he had issues with flights, so he is not going to be here. And so I'm going to, so you get the second team, but he is going to, the work that, the two lectures are kind of very closely connected, and he's going to present his part of the lecture sometime in the near future. So he's going to be doing work speaking about indirect inference, which is an extremely useful tool, which is all related to simulated method of moments as well as just GMM. Okay, so I'm sorry that that's going to be, he's not here to do that. There's a problem set that I have for you on this portion of the class. And so what we're going to do is after the lecture, you'll take a break and all that stuff, and then we'll kind of spend maybe a half an hour or so on helping you through this problem set. And then we'll give you, there's some Julia code that will supply you, et cetera, okay? And then the other part I wanted to kind of say, I don't know all the different backgrounds for all of you. And so I am going to start like from the simplest possible cases and just build up, okay? And it's not going to be, I was saying Erasmus, I feel like I'm doing Econ 101, and he said felt like he was doing kindergarten compared to other people that were doing. So then that made me feel like I'm doing preschool, so anyway, it's going to be simple. I think that, I often think that if you get intuition about stuff, it makes you a better economist or econometrician. So I'm going to try and bring out a lot of the intuition behind a lot of this. Is it working? Okay. All right, and so in that repository, there's going to be several different things. There's like a little syllabus. There are these slides. Then there are two other sets of slides that are kind of bigger ones that I created something smaller from. There's the, the Julia code. And then, so Fatih and I are actually writing a book. And so this is there's chapter 22 of the book is in there, as well as, and the book, chapter 22 is on basically simulation methods in estimation. But the book is how do you do, it's a lot about numerical optimization and simulations and stuff like that. So it's not, if you're interested, contact me and we'll try and get you a draft of the book. Supposedly, we're supposed to get the book to Princeton University Press in January, but I wouldn't hold my breath about that because we're kind of both, I'm slower than Fatih, but Fatih's even slow. All right. So I'm a macroeconomist. Maybe you all are kind of micro people and all that kind of stuff, but at the MBER this summer, actually it's just a group at the MBER, and it's called micro data and macro models, okay? And that's kind of like the way that a lot of macroeconomists now think. We want to be able to talk to microeconomists, applied micro people, and so we often kind of work with panel data sets now, things like that, and cross sections. And so this MBER group really is about kind of looking at the micro data to help us basically estimate the parameters of our macro models, and then to use those models to answer, let's say, policy questions. Okay, so I'm going to kind of give you a little sense of that, how we do that in macro. And then, like I said, I'm going to go into this really simplistic refresher on GMM, because if you understand GMM, you understand the method of simulated moments, okay? And then that's where there will be a problem set. And then Fatih, I'll kind of hint at what the indirect inference kind of stuff is, but that's what Fatih will be doing next week, okay? And So the indirect inference stuff is in that chapter 22 that's in the GitHub and all that kind of stuff. Okay, so here's a macro question, okay? And or the positive question might be something like, how do financial frictions affect the distribution of wealth in the United States? I'm so old, back a long time ago, all we thought about was like a representative agent kind of a world. In a representative agent world, there's no inequality, okay? So we want to think, as macroeconomists, we want to start thinking about how frictions, for instance, affect the ability to precautionarily save, et cetera, and that means how does it affect the wealth distribution? That wealth distribution is an infinite dimensional object, potentially, right? And it's going to be endogenous. So that's the kind of stuff we want to think about. And how does policy change that infinite dimensional object, okay? So, and then once you kind of do that, once you think about that, then you can start thinking, and you have a structural model, you can actually start thinking about welfare consequences. We construct things like consumption equivalence. How far away is the world that we see with, let's say, incomplete markets from a perfect world, a frictionless world? We can answer those kind of questions. If it turns out that it's not that far away, maybe all the costs of setting up the markets to make it complete markets is not worth it, okay? That's the kind of thing you can do. So what we tend to do is build dynamic structural models. In this class of heterogeneous agent models, we put in something like idiosyncratic earning shocks. When I say idiosyncratic, I don't mean it's idiosyncratic across the population. They have persistence as earnings do in the data. And then we feed that into a model, the exogenous stuff into a model, and then it spits out endogenous savings decisions, and then that can be used to generate the endogenous cross-section of wealth. Okay, so this is, since John is going to be coming here, and John is Mr. Nested Fixed Point, I thought maybe I should put this up here. So, the way that macro people, this is kind of, we solve nested fixed point problems, okay? So let me kind of say how, as an application to the one that I was just talking about, the wealth distribution, oftentimes what we do is we just start, like you can go to a data that someone else maybe estimated earnings processes. So, it's really sad because Fatih is like one of the world's leaders on thinking about estimating earnings processes in the US. And actually there's this new depository that he's creating with, I think, some other people, Gianluca Violante at Princeton and maybe Luigi Pistafari at Stanford. So this is supposed to go and kind of create this micro data for for lots of different countries. So you should, if you're interested in that kind of stuff, again, you should be contacting Fatih. But let's take, so someone estimates, let's say, a Markov process for earnings. It's, and this is where I'm saying it's like we're going to assume that it's IID across in agents. That, again, the reason for this is if you had a finite number of agents and they have idiosyncratic shocks, what happens about, so if you have a unit measure of people and you have idiosyncratic shocks, there's no aggregate uncertainty, okay? So here, so often what we work with is, let's say, a unit measure of agents with idiosyncratic uncertainty across the agents. They have persistence in their earnings process, but as long as it's idiosyncratic across the agents, so basically it's like a law of large numbers means you don't have any uncertainty, okay, right? So that's, all right, so that's why we can work in simple stationary models under that assumption, okay? Do not hesitate to tell me, to ask questions, to say you're going fast or not going fast enough, just let me know. Okay, so that was just, I'm going to feed in this earnings process. I don't know if there's a, oops. And then I'm going to use, so the first fixed point problem, you can think of it as being in the middle. You solve for, let's say you solve a dynamic programming problem. So you use a contraction operator. You solve for the value function, and that induces an endogenous decision rule about how much to save. Okay, does that make sense? So that's the middle. That's the middle of this big nest. You take those decision rules. It's a transition. Today, how much will I save or borrow tomorrow? So that's endogenous. There's also the exogenous process for earnings. That's the Markov process. Even if we started everybody out the same, and there's idiosyncratic shocks, it's going to start to fan out, right? Because some people are going to get a bad earning shock and want to borrow. Some people are going to get good earning shocks and they're going to want to save. So eventually, this is going to fan out, and you have to solve for, again, you hope and solve for using another operator. And this operator is not a contraction. So this operator is an operator that takes cross-sectional distributions into cross-sectional distributions. It is not a nice contraction. And so if any of you have read like the later chapters of Stokey and Lucas, that's what it's all about, okay? But under certain conditions, even though it fans out, eventually it just, you get to a nice a distribution that's stationary, okay? That's the second. So now I've used two operators. That's all part of this nested fixed point problem, okay? Once I have that, once I have the cross-sectional distribution and I have the decision rules, I can calculate almost any moment you want me to calculate, right? Because I have, if the model is correct, I can generate, simulated data that is coming from what would be the true data generation process. Okay, and that's going to be really important for thinking about simulation methods here, right? That's how. So I'll get back to that. But and that's what I mean by you can simulate many different moments, and you can compare those to the data moments. Okay, and then we're going to choose the parameters of the model. Remember, all the model depends upon certain parameters. We're going to, the outside loop, and actually I even left one off. There's a loop that you can think of as solving the general equilibrium problem. But outside of all of that, you solve for equilibria as functions of the parameters, but you want to make sure that when what's coming out of the model in terms of whatever moments you want are equal to the data moments. Okay, so you have to pick the parameter values to do that. So you simulate the data, check whether the model moments are close to the data moments. If they're not close, you change the parameter and start all over again. Okay, so that's the big fixed point problem. Okay, yeah.
It says that the zooming thing is not showing the comment.
Okay. All right. Hopefully. Okay, so here, the method of simulated moments, maybe I've seen some other paper out there that's actually calculated for the US the Gini coefficient. I don't know if any people know, the Gini coefficient is a very simple measure of inequality. The higher is the number, the more unequal the country. In the US, the wealth Gini is 0.8. And then if you take a really simplistic model, the best you can do at matching that is about 0.4. So you get half, okay? Anyway, all that's saying is that could be one of my data moments that I put into that I'm going to use to estimate the parameters of the model. The other thing you could do, and this is what indirect inference is instead of, so you could think about, I've seen some other paper this other paper has some regression model that, that's very relevant for the question that I'm interested in about inequality. So it's just like there's another paper. It's a reduced form empirical paper, has no theory in it, but it gave you a regression, okay? And you could ask yourself, can I take my model? And again, if the model is right, it's going to generate a pseudo panel of data, simulated data, and that data should be able to, you could run a regression on that data. And that regression that you run from the simulated data should match the regression that's out there in the world, okay? That's the idea behind indirect inference. It's a very nice, so, when I asked Steve, who's gonna help with the tutorial thing, what was the most useful thing about the method of simulated moments that you learned? And he said, it's that you don't have to have the data. As long as you can find another paper that basically gives you these summary moments or the regression, you can use your model. So for instance, all those people that can't get into the Census Bureau because it takes 6 months to get clearance and all that kind of stuff to be able to get at that data, as long as there's a paper out there that has those moments associated with what you're interested in the census, you're okay with using method of simulated moments. And so that's what is I think, a very useful part of this tool, okay? And by the way, so I'm about to start, really thinking about this. So as a macroeconomist, usually everybody thinks, every econometrician thinks that we're just bozos, because we tend to do what's called calibration, okay? And calibration, is it's getting at the same idea, but not rigorously, okay? So I'll explain to you. As long as you do method of simulated moments, I think the econometricians won't get mad at you as a macroeconomist, okay? All right. So here is, this is why I said, this is I am going to take you from grassroots, okay? So the key thing is, if you know GMM, then it's just a quick move to understanding method of simulated moments, okay? So here's the first example of GMM. It's OLS, okay? So let me be clear. So you can think of, I don't think this thing worked. Yeah, it's not working at a point. Anyway, so, suppose there's, just this linear model. You can think of the beta times xt is the model, okay? And yt is the data, right? And so there's some difference between the model and the data, and that's ut, okay? We often we have assumptions that the expectation of xt times ut is 0, and ut is a mean zero error. And all we try to do when we do OLS is estimate this parameter vector that basically maps this model, beta xt, into the data. And the data is the yt. I know the xt is also data, but it's a beta times xt is a model, okay? So, one implication of the moment condition, that the expectation of xt times ut is equal to 0, is just plug in what ut is, and then that's a moment condition, right? Your standard, that's a moment condition, right? So you're going to be seeing that all over the place. And then if you think about what the sample analog of that moment condition is, it's just, this, okay? Just play around with this and you get your OLS estimate, right? So that's using a moment condition to pin down the estimate, right? Everybody on board? Too simple, I know. Here's another way to get that estimate. Just minimize the sum of squared errors, right? Here you're minimizing the unweighted sum of squared errors of the model, which is beta xt from yt. That's all you're doing. If you solve that minimization problem, take a first order condition, you're going to get exactly the same moment condition that you had before. So which way you do it, it's up to you, okay? The way that we do it in macro, we just form what will be an error vector, a vector of moments that we want to set that equal to 0. And, but we're going to just minimize the weighted sum of squared errors to do that, to find the estimates, okay? So since you all know OLS, you know what I'm about to do today, okay? The other thing is, there's generalized least squares is basically a more general moment condition than what we had in 1, where, you're upweighting or downweighting the errors by some measure of the variance of the data in the data, okay? So if the data has a lot of variation in it, you kind of downweight the estimate from that, okay? And you'll be seeing that, you'll see that in the weighting matrix that we use in GMM, right? Any questions? It's really simple. Okay, so here's how macroeconomists kind of, and this was the application that Lars Hansen, used when he wrote his Econometric paper on GMM. Okay, there's a paper by Hansen and Singleton, and this is basically a simple version of that. Okay, so this is where you get to see, I have a model. Right? This is Bob Lucas's famous equilibrium in the stock market kind of Econometric paper, but all it was kind of saying, I'm just going to maximize the expected value of a representative agent's utility. The person's choosing their consumption and what stocks to hold. Their income is YT. You can think of the income being derived from a tree that's giving out these dividends. The price of the stock is PT, and the number of stocks is ST. So the right-hand side is what, the value, basically it's like my dividends and the current value of my stock portfolio. The left-hand side is my consumption and any stocks that I buy or sell in that period. Okay, simple. This is like your first year macro class, right? You have to have market clearing for a general equilibrium model. The dividends, YT, are all paid out as consumption. And we just assume that there's a stock of stocks we normalize it to 1. So then, what we do in macro typically is we parameterize things like the utility function. So there are 2 parameters that are going to be in this model. It's going to be, let's say, the coefficient of relative risk aversion, psi, as well as the discount factor, beta. Okay? All that I have here is a first order condition. Okay? If you take the first order, plug in CT from the constraint into the utility function, take a first order condition with respect to ST plus 1, and you get this. Okay? This is the cost of buying more stocks today. I don't get to consume as much. This is the benefit. I get a higher value tomorrow. Marginally, we're weighting all these things by the marginal utility, but it generates a condition that looks like this. Okay? I just rewrote 7 here. Okay? Now, what this says, and this is why this is GMM. This is, you can think of this as here's a moment condition, right? It has to be the case that the expected value of this first order condition is equal to 0, okay? But that's just like that moment condition I had before, right? Okay, so I have one moment condition, and I have how many parameters? Remind me. This is at the end of the day, so I know you guys are going to be tired and don't want to be thinking about this, but so I'll try and ask questions. But if you don't know the answer, it's okay, and we can talk about it over a beer or whatever. So how many parameters do I have? I have 2. I have beta and I have psi. And how many moment conditions do I have? 1. So, there's something called order conditions for identification. We're in trouble, right? Because we have 2 parameters, but it's like I have 2 variables to solve for in only 1 equation, right? First, like kindergarten math, right? So that we're in trouble. Maybe not kindergarten. But so I'm just rewriting this in terms of errors. So the data is the xt, b is the parameter. So b is a vector of 2 parameters, and we're this is an error, and we're going to set this error equal to 0 on average. That's what GMM does. Okay. Now so let's just count. I'm just kind of going through this again. Let's count stuff. So I have 1 error. N is equal to the number of moments. I have 1. My parameter vector is 2. That's little l. And then k is some vector of variables, let's say 3, because I have to, I might see consumption, income, and stock prices, or consumption, dividends, and stock prices. Okay? So, the problem is we're trying to estimate the L equal to 2 parameters to solve 1 moment condition. We're in trouble. Okay? So, let's see, okay, so and now let's just kind of generally say, suppose there are n necessary conditions. So now U is an n by 1 vector of, let's call it errors, that first order condition that we had before. Since I'm heading towards method of simulated moments, it's just going to be the errors in method of simulated moments are just going to be the difference between the data moment and the model simulated moment. Okay, but that's an error. Okay, just like this is an error. Okay. So if the number of parameters, which is L, is less than the number of moments, then the model is over-identified. If it's just equal to, it's said to be just identified. If the model is has more parameters than equations to solve for it, it's said to be under-identified. Okay? And so obviously we're in the under-identified case right now because we have 2 and 1, trouble, okay? So the really smart thing about that these guys did, Hansen did, and they showed in this example, is, I just have to add more equations, okay? Because I have 2 parameters and I need another equation, for instance. So you just kind of take anything else that's in the information set of the econometrician, and that can create another moment condition that you need. Okay, so what they did was, they used, this is the first moment condition, but they also checked whether the consumption growth in the past, how it was correlated. They can use that as another moment potentially. It's like an independent variable. And it creates another moment. Okay, so this is just to bring, to say in Hansen's paper, you would see a more general thing than what I'm about to do, which can take into account all these Kronecker products, et cetera, et cetera. But this is just to keep things simple. Okay, so what GMM does, remember, is I have this error, which is U. I'm going to take the unconditional expectation of that, and that's a function of the parameter B. So we're going to be taking this unconditional average error. At the true value of the parameter, it's 0, right? Because if the model is correct, is true, if I've got the right parameter value, that expectation is equal to 0. Okay? Everybody agree with that? Because this is like a fundamental thing. Okay? All right, and just like I had before, you know, we can get sample analogs of these moments, right? And the basic idea is that, you know, this sample analog, if I have enough data, is going to get me to, you know, the true parameter value, okay? And that's, you know, so remember, this is why I kind of did this stupid OLS stuff. This is exactly the analog of that first OLS condition, the moment condition, okay? Now, remember I showed you there's another way to get the parameter value, and that's by minimizing, in the OLS case, it was not a weighted sum of squared errors, but here we're gonna just minimize. Remember, this G function is, you know, an expectation of the errors. So we're just going to construct an objective function. It's going to be the weighted sum of squared errors that depend upon the parameter values. And you know what's going to be important, and what I'm going to try and kind of bring through to you is the weighting matrix matters a lot. Okay. So right now, just to put it this way, think of it as an arbitrary weighting matrix, and then this is the analog, the minimization problem that we did for OLS. Okay, so just to keep on getting some intuition. You know, if you're in the just identified case, the weighting matrix doesn't matter at all. You should be able to minimize, if the model is correct, et cetera, basically under most conditions, you should be able to get to 0. Okay, and then the weighting matrix doesn't matter. In the book, you'll see a little example to show you that. Okay, and so what Hansen did was, theorem 2.1 proves that the estimator exists and converges in probability to the true value. It's essential for consistency. So now we're kind of focusing on the consistency part, that there's a unique maximum in or unique minimum in the that should be minimum at the true parameter value. And that condition is related to identification. And then furthermore, Hansen goes out and establishes asymptotic normality of the estimator. So this is all stuff that I'm sure you have gotten in your GMM, your econometrics class, right? Okay, sorry, but so here are the consistency conditions, okay, that we were talking about. This is in his paper. These are the ones. And the second bullet is really kind of like the really important one, and the continuity of the errors for each parameter value. When you think about the stuff that's really going to make it difficult to estimate things, it's kind of those two, because the second condition is sort of known as global identification, and that's almost impossible to verify in general. Okay. So there's something like a simpler necessary, but it's not a sufficient condition. That's known as local identification. So, and it's basically related to like taking how much the change in the parameter value changes the objective, okay? But this is all gonna be a local kind of argument. And that's based off of taking a Jacobian of this vector GB, okay? And so this condition, local identification, is that once you take the Jacobian matrix, you must have full column rank, okay? And again, I know you guys all know this, but it's just good to see it again and again, maybe, to keep it in mind. But if for instance, one of the columns has no impact on the objective, right? Then the Jacobian is not going to have full column rank. And so then it's basically saying that the estimate is not very well, the model is not well identified, okay? All right, and I'll come back to that in a little bit. And then there's, that was consistency. Now, the one thing about the consistency part to keep in mind is that nowhere did I say anything that all I needed was that the weighting matrix be a positive semi-definite matrix, okay? I didn't have to say anything about, it could be kind of anything, and I'll still get a consistent estimate, okay? And that's kind of important for thinking about this stuff, okay? So that's consistency, but then when you start thinking about efficiency, then, you know, Hansen has this, has another theorem in his paper that the statistically optimal weighting matrix is just given basically by the inverse of the asymptotic variance covariance matrix, okay? And then, so remember GLS before? And so if you kind of think about this, since we're taking the inverse of the variance covariance matrix, if you have a lot of variation and you're taking its inverse, that's downweighting things, right? So this is just kind of the same kind of idea as what was behind the GLS stuff, okay? All right. And then, you know, the problem is that, you know, we don't know the true variance covariance matrix or anything like that, so we're going to do this in a small sample. He goes out to show, you know, other properties. This is a consistent, you know, that the variance, the estimated parameter, you know, there's a consistency condition that is unbiased, and then also he calculates what the variance of the estimate is using the optimal weighting matrix. Okay, and so this is just again what I was kind of trying to say before. If you look down, you know, here I have you know, this is the Jacobian. Okay, so in this Jacobian, right, is going to be related to, remember this is all like inverted, this is going to also impact what the variance of the errors are, okay, of the estimate. Okay, so if the, you know, so the precision of the estimates is related to this Jacobian. If the objective is very sensitive to changes in the parameters, i.e. that derivative is high, then there's going to be low variance in the estimate because we're doing all this inversion. If the objective is not very sensitive to changes in the parameters, it's going to produce a high variance for the estimates. And so, you know, like if you find big standard errors, it's probably because the objective is not very sensitive to changes in the parameters. So it's hard to find the true unique maximum. It's just like when you kind of think about it graphically, here's a high variance of, you know, a high derivative. Here's a low derivative. If it's just saying that the surface of the minimization objective is just very flat, if that is very small, okay? And then that's kind of saying, what is B, right? If you're here, it's not clear which B is the right B, right? Here it's pretty clear what's the right B, okay? So just kind of keep that in mind. What else? Okay, and so, you know, that's how local identification is going to be linked to standard errors. All right, and then so how do you implement this? Well, you can kind of think of, even if you don't, so suppose you, so this is where I kept on, to make Steve happy, you know, suppose you don't have the data. So you don't have the data to actually form the optimal weighting matrix. So then what could you do? Okay, so now this is a real question for you, and I will give you a hint. Remember, any weighting matrix gets you a consistent estimate of the model that you're going to assume is truth. So, well, you could take, if you get the consistent estimate, you could then take the model, generate a pseudo panel of data, and then estimate the weighting matrix off of that, right? Does that make sense? So that's a sense in which, you know, the simulation part, it's very useful, okay? All right, so that's all that this is kind of saying. You know, the first stage estimate, you get a consistent estimate of B, then use B to estimate, you know, like to construct this panel, construct a variance-covariance matrix, and then use that in the second stage to estimate, you know, your weighted sum of squared errors, okay? So, and that's kind of like a two-step procedure in generalized least squares. Okay, so so are there any questions? I'm supposed to go till 3. Oh, I'm doing really well on time, actually, okay. So,
How do you think about like whether the global identification is a big problem? Like, if you don't have global identification and there's multiple parameters that generate the same moments,
yeah,
and that's all you care about is getting those moments.
that's why it's almost impossible.
Yeah.
Thinking about global identification is almost impossible. I think forming, like one thing that we do a lot is just kind of take our model and then play around, like just try and create the surface, right? And if you create that surface, you can maybe see local minima and all that kind of stuff. So, you know, as long as it's a pretty sparse, you know, you don't have a huge multi-dimensional problem, it's not so hard to create that surface and get an idea, okay? The other thing is, you know, and I was talking to Fatih about this right before I came here, you know, this one way to kind of always think about solving these models is kind of think of a simpler model and which is, you know, it might be easy to show is kind of globally identified, and then, you know, build from there, okay? And that's kind of one of the things, but kind of doing these little perturbations of the objective function, and then there are, you know, that's kind of like a local approach, but then there are minimization routines like, you know, simulated annealing and all that kind of stuff that kind of gets you in lots of different places to kind of figure out where you are with the objective function. Okay, so remember that the moment condition was just that the errors, you know, we were basically minimizing the weighted sum of squared errors, okay, in GMM. So now, and again, this is kind of getting at some of these ideas. So suppose you don't have access to the data, or suppose that you know, that first order condition that I had that was, you know, from the Hansen and Singleton model, you know, once you put in something like a borrowing constraint or some kind of an inequality constraint that it can break those first order conditions. So then that first order condition is no longer very well behaved, okay? And so, you know, then it becomes really hard to evaluate that vector valued function that I was calling U. So, you know, instead we're going to construct the errors via simulation methods, and we're only going to be using like relevant moments of the data, and that's where, you know, you could get some moment from the data from some empirical paper that you had no hand in, as long as you trust the moment, but you can grab it from someplace else. So you don't actually have to do the dirty data work, okay? So that's, and you know, then you compare your model moment to that data moment, okay? And the difference between the model and the data is an error. And that's what we're going to minimize the sum of those sum of squared errors, okay? That's all that, so it's just that simple. That's what method of simulated moments are. The only thing that we're doing is we're using the model here to create a simulated panel of data that we then construct the model analog of the data moment, okay? It's that simple. All right, and you know, the reason why I spent time on GMM, and I'm only going to spend like 3, you see, it's only a couple of dots there, is because if you know GMM, you know SMM, okay? Okay, so this is like kind of being a little bit more formal about it. So, you might have the data, which is xt. We're going to assume that that's a realization of some vector-valued stationary and ergodic stochastic process. Then we're going to let the model data be a realization of, again, the assumption is that it's stationary and ergodic. And the ergodicity is kind of important for, as long as that holds, then even if you have like a sample of 100 data points, as long as the process is ergodic, you can kind of resample. So you can take lots of samples, H samples, of 100 periods long. Okay? Does that make sense? Okay? And then, this is where you can construct data moments. You might not even have to have the data, but you just have the data moment. You construct this, you do construct model moments. And I was saying you can take, the simulated data can be of, in some sense, length h, which is the number of replications of the t period sample. And then we're going to be assuming that, the population moments exist, basically. You can think of it that way, okay? And then here's the most important part of this. It's basically that, you can think of it as the null, that the model is correct at the true parameter value, then the population moment from the data has to equal the population moment from your model at the true parameter value, okay? And, I kind of put a smiley face there because I think this is like a really important thing for thinking about economics, because it's kind of saying, the left-hand side of mu of x, that's data. The right-hand side, mu of y of b0, that's model. And so this is linking model and data. And, there's this famous thing called the Coles Commission, and they kind of, and I think, that's kind of the backbone of the Econometric Society. They focused on linking economic theory to math and statistics, and that, their motto was theory and measurement. But that like, as a macroeconomist, I realized we have to live by that. Okay, we have to think theoretically, but we also have to. We just can't do it in a box. Okay, so it makes it harder. It also probably makes it harder for IO people because they can't think. They take structural models a lot of times to the data. There's lots of different disciplines that are doing that, but it means you kind of have to make. Unfortunately, you have to make a lot of different referees happy. Okay, which can often be hard and take a long time. Trust me, I just published a paper that I started working on in 2004. Okay, so I'm very, very slow. Okay, luckily no one else could figure out how to do it either. So, okay, so. So then, here is we're just constructing the weighted sum of squared errors. It's kind of here, we'll just think if there's any weighting matrix. There's lots of different papers that kind of show that, basically this is an application of GMM. So this paper by Lee and Ingram is the shortest one. It's in the Journal of Econometrics. It's probably like 5 pages. But basically it just goes out and applies what Hansen did. The assumptions you need are basically the assumptions that Hansen had, okay? So anyway, so the bottom line is, you see, I'm just minimizing the weighted, MT is the data moment, MN of Y of B is the model moment. Whenever, as we change the parameter value B, the model moment's going to change, and we're trying to get it closer to the data moment, right? And if it's not, if the parameter value doesn't really change the model moment, then we have that flat surface, right? And we have a little bit of an issue. Okay, so again, this is just kind of, you can think of how do you solve this problem. Remember, we're using simulation methods. So, it's basically like two steps. The first step is for any parameter value, let's say B in iteration I, you have a draw of the shocks, okay? You do H draws of the shocks. You have to use the same draws, okay? And let me go through this and then you'll see why. This was when I did, so you take these draws, then you feed it into whatever, the model is. So I was kind of saying it induces technology shocks and decision rules, the kind of the stuff, earnings shocks and decision rules, like I had what I was talking about before, and that induces a realization. Here I was kind of thinking of real output. It could be a realization of, the distribution of wealth. Okay, and then you compute model moments based on those, and then you evaluate the objective function. You just keep doing that until you can't make it smaller again. But then this is again the issue about there could be local minima and things like that. Okay, but that's the idea. Okay. So why is this? Why did I say you have to use the same draw? Because, if you change the B, you're going to change the errors, as well as it's kind of nicely identified, right? But if you both change the B and you change the errors, you don't know where, it's coming from. If you drop things, it could be coming from a change in the errors. Okay, so you want to keep the same errors and just feed in and search for the different B. Okay, everybody agree? Okay, so now I'm done with the theory. All right, now I don't know about you guys, but I work better by seeing examples. Okay, so I'm about to do an example for you, because this is all kind of general. Okay, are there questions on anything? Yep. Yeah.
You need like several simulations for each parameter to compute them.
No, I'm going to take 8. I'm going to simulate. I'm going to draw epsilon from some distribution t times. I'm going to do that once. I'm going to do it again for another one. That's h equal 2. But I'm going to keep that set of errors. I'm going to feed the same errors in to my model, but I'm going to be changing the B.
Yeah, so you simulate, like, for each T, you simulate, say, 5,000 different errors. And then you let that through T, and then you keep those and repeat for each type of parameter.
I'm only keeping the epsilons,
yeah, and
right?
repeat across parameters.
That's going to induce a realization of the things, the variables of interest. Yeah. And every time I change the B, I'll get a different realization of the values of interest. But if I was changing the epsilons, I could get a different value.
If you change the epsilon, you change 2 things.
Yeah, well, if you change the epsilon, you're changing 2 things at one time, and that's not a good idea.
For the difference between GMM and MSM, I've been thinking of it as GMM have theoretical moments that we want to be like the data, and method of simulated moments have these simulated moments we want to match to the data. Is that a right way to think about it, or?
Yeah, I think that's fine.
Okay.
Yeah.
Great, thanks.
Okay, any other questions about All right, so I am about to do the simplest possible model or example that I could think of, and you're going to have to do this on your problem set, okay? Not this exact one, but a little bit different, okay? So, and this is basically from a paper in the Journal of Econometrics. They were just trying to see what, several different simulation estimators, what's the best one and properties of it and all that kind of stuff. So this is out of a paper in the 2000 Journal of Econometrics. The example I'm going to do, they did some this is a different example than the ones they did, but the idea is identical. So I'm going to think about there being, like, instead of a macro model that's really complicated, I'm just going to take the true model to be an MA1, okay? That's why I said this is like the simplest possible data generation process, okay? So it's an MA1. There's one parameter, B0, and then the shocks or epsilon t's are going to be, I'm going to assume they're normal II01. So, in the terms of the stuff I was doing before, there's, one variable, which is this MA1X. There's one parameter, that's the L, okay? And then the model, so I'm going to say that the model generation process, suppose I know that the true model is an MA1, I just don't know the parameter, okay? So that's why I don't know what B is, right? This is like doing almost like a Monte Carlo, right? I know what I'm about to do, so I can play with everything. But so I know the model they're both it's not misspecified. It's an MA. I do know it's an MA1. I just don't know the parameter of the model. Okay. Okay. So that's all. So I'm just gonna go out and try and estimate the parameter model using simulated method of moments. Okay. So because I know the model, and so here's let me just suppose in general, you don't know. You go out into the world as this econometrician, and you don't know what are the right moments to use. Okay, just like I'm trying to make you think about things. Okay, so I'm going to be like a stupid econometrician. I don't know what moments I should be using. Right now, I know that I need this thing to be, at least identified, but I'm going to consider a case where it's over-identified. Okay, so I'm going to think, remember, I have one parameter, and I have, I'm going to say that there are 4 moments that I think are important. Okay, and I think I'm just hoping that this gets you to understand, some of the identification issues. Okay, so I'm going to say, in some sense, you can think of it as the mean, so ZT. So this is going to be, I'm going to construct from either from ZT could be either data variable or the like simulated data. Okay, I'm going to think about constructing 4 different moments. Remember, I need n greater than or equal to L. So here's 4, the mean, the variance, the autocorrelation. This is an MA1, but I'm using the autocorrelation because I just don't know, okay? And also the second order autocorrelation because I don't know, okay? This is an illustrative example, okay? Now, if this is, these are the 4 moments I'm kind of thinking about, this should be L. If this is the 4 moments I'm thinking about, but I know the true data generation process, I can calculate the true variance, the asymptotic true variance, and all that kind of stuff. Okay, so here it is. Okay, this is just the oops. The first one is just the mean variance first order autocorrelation, second order autocorrelation. You guys are going to have to do this on your little problem set, okay? You know, all that I did here was just, you know, take square stuff, etc. Okay? But, you know, and then once, you know, you can kind of see, once you start squaring stuff, like this expectation, this is just 0, right? This is just 0. So the mean is just going to be 0, as you would have expected. It was a 0 mean MA1, right? And there's going to be this is not going to be 0. Why is it not going to be 0? You know, here's variance terms, right? Okay, so I'm not going to bore you with this. Once you plug in all this stuff, here's that, here. So this vector is nothing other than, we saw that the first term should be 0. There's your 0. There's another term that's 1 plus b squared, the true b. The other one is minus b, and the final one is 0. Okay? Now, that's from the data. This is from the model, right? So now, hopefully, so what I'm trying to get at is, can you get anything out of the mean for estimating b? No, right? Can you get anything out of the second autocorrelation? No. The thing that's kind of interesting, you can get something out of the variance, but what do you get? What's the issue there? You don't know its sign. It could be negative or it could be positive, right? And then this autocorrelation, you do get something out of, obviously. Okay? So I just want, you know, this is to give you some intuition for how different moments might not, you know, be informative, right? Okay. Now, this is where it's going to get a little wonky because, well, okay. Anyway, yeah. Yeah, so that's a good question. Let's talk about that after, because it's a long, I don't have a good answer. And yeah, that's an important question. Okay. But you know, so here, you know, this is just kind of the foundations for that. You know, here's the sample analog of the errors. Okay, the data moment versus the model moment, and all we're doing, you know, the error vector that depends upon b is just, you know, in the you know, this doesn't really matter because we're doing the asymptotic stuff, but basically it's just going to be the difference between the data and the model population moments. Okay, so, you know, this just kind of goes to, you know, kind of saying something about global identification. These have to be equal, that has to be equal to 0, so the two have to be equal to 0, so now you know how you can pin down the parameter estimate, right? Okay. This is the wonky part a little bit. So we're going to eventually, remember in the GMM stuff, we wanted an optimal weighting matrix. So we're going to start thinking about the optimal weighting matrix, okay? And I don't want to spend a lot of time on this because, yeah, I don't want to spend a lot of time on this. So, but because I do have a lot of little dots still. So remember, we wanted, you know, the optimal weighting matrix was going to be the inverse of the asymptotic variance covariance matrix. Here's just a statement of the asymptotic variance covariance matrix. And you can show, so because of because of this, you know, that they have to be, you know, basically the models have to be equal. It doesn't matter whether you use it from the data or the, and that's, you know, this is just restating it, or the model, okay? So that's just in asymptotically. And then here's where, you know, this is where I said, like, you know, you can play around with a piece of paper and pencil, okay, and you're going to get something that looks like this, okay? So the asymptotic, the optimal weighting matrix for this example where I've evaluated it when B0 is equal to 0.5, just comes out to be, look something like this. I know this is like kind of behind it, so it's not, you're going to understand this when you do this problem set, okay? All right. So, and then, now let's say I have this optimal weighting matrix. I'm going to form a weighted sum of squared errors, take the first order conditions, and here is the first order condition right here. And when you see the first order condition, you kind of get, you can see that, that rank condition. This is not a vector of zeros. Okay, remember that was from before? Okay. And if you know, this, I'm just plugging in the optimal weighting matrix. I'm plugging in the derivative there. And then, you know, basically all I'm trying to get you to see here is that, you know, we basically have one equation and one unknown in the end to pin down what B is, okay? Just, if you like just one equation and one unknown, I got it for you, okay? Everybody cool with this? This is just simple stuff from, everybody, you see what I'm doing, right? Okay. Okay, so here, like, but I think this is kind of interesting, because I've put in the optimal weighting matrix, okay? And you see, like, there's a 0 here, okay? So I kind of go, what does 0, all these things imply? Remember, this is an over-identified system. The mean didn't matter, okay? So that's kind of why there's that 0 there, okay? The most weight is placed not on the variance, because remember the variance, there was an issue about multiplicity. Okay, I'll get it in one sec. But the most weight is being placed on the autocorrelation. Okay, and then the interesting thing, because I'm saying the weight, like you've got 0, 0.45, 1.29, and 0.67. Remember, the second autocorrelation should not matter, okay? But the issue is that the second autocovariance doesn't depend upon B, but it is correlated with the variance, okay? And so, so it, you know, has some relevance, and it has some weight, okay? So it is informative. Not directly, but indirectly, okay? So you had a question? Oh, okay, yeah. Okay, and then, you know, again, this is just using Hansen's theorem 3.2. You know, again, this is where that, you know, rank condition comes in. It's not a vector of, column vector of zeros and stuff like that. And then, yeah, I mean, that's all, this is all just applying what's in the GMM stuff that I showed you before. So this is just how do you compute the standard errors, et cetera. So here's but remember, everything I've done right now is just asymptotics. And, you don't necessarily know that, right? This is where we're heading toward. So what's important is the small sample properties of this stuff. Okay, so that's what we're going to do right now. So, so I'm just going to, I'm going to kind of think about constructing a sample of 200 periods. So this is just the true data, because I know that true data, the true data generation process. I just draw a random sample of the epsilons, and then I construct a 200 period moving average process. Okay, and then I can compute the the mean of the small sample. The mean of the small sample, in the data, 200 observations, it gets pretty close, but not, this is why there's sampling error. Okay? So, this was supposed to be 1.25. It's not. This was supposed to be 0.5. It's not. And these were supposed to be 0, and they're not. Okay? I can also construct basically the variance-covariance matrix from this small sample. This is that variance-covariance matrix, and you can see it's not exactly what the asymptotic variance-covariance matrix is. Not surprising, right? So that was the data. Like that's, if you had the data, that's the data. We're assuming that's the true model data, the true data generation process, okay? And so the true data. So now we're gonna kind of do the same thing, but we're gonna do it with the model, okay? So we're gonna draw a series of, H. This is like getting back to the first one I draw 200 observations. I set that aside. I draw another 200 observations, set that aside, set it aside, up to H. We did H is equal to 10, okay? And then, I can construct a simulated model moment. Remember, there's 4 of them. I can construct that off of this data, okay? And then all we're trying to do is choose the parameter B so that the weighted sum of squared residuals between the model moments and the data moments is minimized, okay? Estimation procedure depends on what the weighting matrix you use is. I'm just going to start, and I'm going to show you how, how this varies, how this affects the estimates, the choice of the weighting matrix, okay? Okay, so if I use, this is the part where I was saying I'm going to show you how, if I use the true weighting matrix, right? Because that's off of the data, okay? I constructed that one here, like it's just the inverse of this thing, okay? And then I use that here, and then I put it into a minimization routine. I get 0.4993. Okay? Now, if I could do something different, okay? What if I had just, instead of plugging the optimal weighting matrix here, I just plug in a identity matrix, okay? And I minimize, and then what do I get? I get 0.485, okay? Now, what if I do that two-step thing where I get this, I then take my model again, and I use this estimate because this is, it is a consistent estimate, right? I use that logic. I take this, I plug it into the model, and now I generate a variance-covariance matrix off of that model. It's like I'm doing this two-stage, right? I got this from a first stage, and then I construct a weighting matrix from that first stage, put it into the second stage, and I estimate this problem. Okay? What do I get? Well, I get 0.4970. Okay, so this is an example. This is just a very simple example, but you can kind of see how the weighting matrix does kind of matter. Okay, so just using something as simple as an identity matrix, we get pretty close, but you can do better from doing this like two-stage thing. Okay, yeah.
Would it make sense to do it again?
Yeah, you can do like there are routines that do it many, many times. Yeah. The problem is in macro, our models are so like first of all, they're so big, and second of all, they're so wrong that it really doesn't matter that much. I wouldn't do it many times. I guess I'm going to get in trouble with my co-authors. One of my co-authors is this guy, Victor Rios Rule, and he's at Penn. And he says, if you don't believe in your model, just don't waste my time. So I do believe in the models I write down, but they're simple versions of the world. So anyway. Okay, this is just, because so your problem set is going to be two-dimensional. There's two parameters, but here there's only one parameter, so here's just a graph. This is where I used, you can't see this very well probably, but this is where I used the identity matrix. And if you definitely can't see it in the back of the room, but this minimum here is a little bit different. This is where we use the optimal weighting matrix, and you can see it's kind of pushing you closer to what you want it to be. You can compute standard errors. This is what the basically like the gradient or the Jacobian for this particular case is. It's really, you can see it's pretty darn close to the true. This is the true Jacobian. Okay. Yeah. Usually you have to just do finite differences to calculate numerical derivatives like this. And all I was trying to do here is kind of show you, if you remember, I kind of said if your standard errors are big, it's kind of saying that something's maybe a little bit wrong with your model. So you can kind of kind of look at this is using the in some sense true small sample estimate of the variance covariance matrix. The top one is using the estimate that would come from that two-step procedure that I was talking about, where you don't actually have the data. And you see that the standard error is a little bit bigger in the second case. And then, you can go out, once you can kind of use, a J-test to test whether your model, is right? And so, this just gives you the formula for computing that, and, basically for this simple example, you can't reject the hypothesis that the model's true. Okay, so you don't have, because you're doing simulation stuff anyway, you don't kind of have to, remember, you're constructing here you're constructing standard errors, off of, off of the model, all these Jacobians and estimates of the weighting matrix. But you can just bootstrap stuff, right? So that's another way. So the thing that, I will say, being an old macroeconomist, the thing that most, whenever the micro guys, applied micro guys see our stuff and they say, where are your standard errors? Because that's, like calibration, the original stuff had no standard errors or anything like that. Okay, so that's why we are kind of like junior, kind of stupid macroeconomists. And that's what, calibration was just, simulated method, just so that it's clear, simulated method of moments is just a more kind of rigorous way. Nowadays, people, kind of minimize some weighted sum of squared errors kind of thing, and they call it calibration sometimes. In the old days, a lot of times they would just get a model moment or something, and they would, people would say, oh, the model version looks pretty close. When I just plugged in this parameter value, it looks pretty close to the data moment, and kind of stop. Whereas here, you're not stopping until, your criterion is minimized, okay? So it's really very similar. It's just like calibration is baby SMM, okay? But, you can, instead of getting standard errors the way I was just doing it, you can just bootstrap this thing. And this just kind of gives you, we basically bootstrapped it. You can kind of see, remember, the standard errors that I had here, it's bigger. The data is smaller than the model-generated ones. And this just kind of goes out and shows you that. Okay, yeah?
Question, how do you bootstrap the data one here?
It's because I know, yeah, that's the...
Otherwise you will need to block, right?
Yeah.
How you get the MA.
Yeah. Okay, and this was just a kernel estimate of that. Yes?
Sorry, before bootstrap, so when you say for the example that you did where you have 4 moments to estimate one parameter in like this over-identified system, it reminds me of the multiple equation GMM, but correct me if there's a clear difference between them. But like when I think about over-identified systems, like my first reaction is the more moments that you use, you have this worry of contagious model misspecification.
Yep.
And when doing, like, how do you think about it in
So that's
this?
where I kind of think you two should be talking to each other. Because, the question about, what are the right moments to be kind of focusing on, too many moments is getting at the problem you're talking about, right? So, but what are the right ones? And that's kind of, so what I was kind of hoping that this example shows you is there really are some right moments, but often we don't know what they are. That's kind of the problem for a lot of us. That's where I feel like, using economic theory is important. It's also when you want to try to explain to people what's going on in your model, you don't want to be kind of focusing on moments or summary, let's just call them summary statistics that aren't very relevant for the question at hand. So let me say this in a different way. We all knew, everybody knew just off the bat that the mean was irrelevant, right? If I had asked you the question at the beginning of all this, because it was a mean zero MA1, it has nothing to do with it. So you would have all told me that's just a stupid moment that you put in, right? But it was there to kind of explain, to kind of show you. What is a little surprising, right, is that asymptotically the third moment or the second autocorrelation doesn't matter, but in small samples it could be helpful. That I think is another thing to kind of, in answering the question. This is something that theoretically should not be helpful, but maybe in small samples it helps you a little bit.
Does that positive weight of the fourth moment, is that something to do with, like, does it have, like, efficiency gains if it's included in the joint estimation?
Yeah, it should, because that one was using the optimal weighting matrix, and that was the efficiency gains are coming from using the optimal weighting matrix. Okay, so let me it is really kind of time to conclude. So let me summarize by kind of saying, if you know GMM, you know the method of simulated moments. By the way, I always call this simulated method moments, so when you read it, sometimes you'll see simulated method moments, but I think like McFadden was one of the first people to do this, and he called it method of simulated moments. So it's either one, okay? And it's kind of super useful if you only have access to empirical studies providing sample moments, or it's really difficult to evaluate, like that first order condition I wrote. If you have binding constraints and things like that, it's not, you have this multiplier that kind of drives a wedge in there. It's not really well defined kind of thing. So it's very useful when you have that kind of, it's useful in discrete choice problems as well, okay? So Fatih is going to do this stuff on indirect inference. So let me just kind of say, I kind of think of, like the example that I would use is that indirect inference, there's this, what they call an auxiliary model. And the auxiliary model is just something that could be just a reduced form regression. But you want your model to be able to replicate what's in that reduced form regression. Okay? Now, it's the same, what is a regression coefficient? Right? It's a covariance over a variance, so it's a function of moments. Right? So it's like the same, once you understand that, this is all kind of the same thing, okay? But the nice thing is, it's a really useful, like indirect inference, you go out and you find your favorite empirical paper that's relevant for the model you're going to write down, and you just use those regression codes. That's your auxiliary model, okay? That's what the indirect inference part is. So, you're trying to, again, it's instead of taking the model moments and the data moments the way I had it here, it's like basically you want your model to generate what's in the auxiliary. You want your true model to generate what's in the auxiliary model, okay? And you choose the parameters to get as close as possible to that, okay? So he's gonna, he and Tony Smith and I think Montfort, Guriot and Montfort, they were kind of this, Fatih was Tony's student, and they've written a really nice paper in Econometrica on using indirect inference. That's next week, and Fatih's a great lecturer. You will enjoy it very much. So, all right, so I'm done with this part. We should take a break and then maybe come back and just take half an hour for these. We'll show you the stuff that you have to do for the problem set. And yeah, if you really want to go and have a beer before that time, then it's going to make the problem set harder.